Welcome back to the Earth Science Classroom. Hi everyone, how are we doing? So we are looking at how to locate an earthquake. So earthquakes happen all across the world. In particular, America has certain areas that are, more prone to earthquakes than others. Obviously, you need fault lines, you need fractures, you need movement, you need plate tectonics, you need convection currents, moving plates either away from each other and divergent, which is not really a part of the United States makeup of tectonics. That's more in the ocean and the Pacific. But we do have some transform plate boundaries and convergent plate boundaries, most likely in the Northwest, in Washington, Oregon, Northern California, and especially with the transform plate boundary, the San Andreas fault line and fault zone system out in California. So we have certain areas, obviously, with our convergence, ocean with the Juan de Fuca plates and the North American plate. We have our transform plate boundary here with the San Andreas fault system. Not so much a line per se, but there is the main one, and then there's other smaller parallel or perpendicular fault lines and fault zones coming off this all the way for the 800 miles that it goes off into the Mendocino fracture zone off in the Pacific Ocean. So then we have as an area here, the New Madrid seismic zone in Kentucky and that area. Then we have some seismic activity with the fracking, unfortunately, in the Kansas, Oklahoma, and northern Texas area. So we do have pretty much a lot of the country has the potential for earthquakes, some more than others. And when an earthquake does happen, the USGS and other agencies and federal and town and district and state governments want to find out where it happened quickly so they can get to help people put together the infrastructure or maybe put in place communication and to minimize damage and obviously save lives. And the faster we can locate these earthquakes, the faster we know how large they are and how they're going to affect the area, kind of rock and bedrock it's going to go through, the kind of population density or area it is based on the location. So it's important. Now, how do we do it? All right, so you need 3 different sizes. Each one must be from a different location. Let's just say the earthquake happened right here. Okay, we'll just say it happened here, right? Example, right? Here's my epicenter, EPI. Okay, and then the waves come out 3-dimensionally, spherically around. All right, okay. All right. So all the waves, the P, the S, the L, and the R, all released at the same time, and because the P wave is the fastest wave, it will reach. So let's say there's a seismic station here, you put A, 1 here, B, then you have point C. So you have these 3 separate locations, all experienced, registered, and collected data on this earthquake with the shaking in the seismograms. And you could, in theory, there could be thousands of seismic stations all around this area, but you choose 3 in different areas, basically to triangulate. So what you want to do is triangulate the position of the earthquake epicenter. Now, triangulate means 3, so you need a minimum of 3 seismic stations of which you take the seismogram data. And what you take is the time difference, okay, between the S wave arrival and the P wave. So you take the S wave, subtract the P wave, and you get the time difference for each 3. So let's say the first one, right? Let's just say that you have, let's just take these and put it on the map, okay? So take this example, and let's have A be in New York. So around here, okay? Vaguely around there, New York, New Jersey. Let's have B be in Chicago, right there. And let's have C right here, or close there in LA. All right. Or not LA, let's say Northern California. or Central California. So you take these locations, and let's take for each one, you take the time difference from the S&P arrival time. So let's say the time difference for New York, New Jersey was, let's say, 9 minutes. Chicago was 7 minutes. Again, difference between the S&P wave, add that exact seismogram. And then Central California, let's say, is 1 minute. And these times relate to the distance. So let's say New Jersey and New York, 9 minutes equates to, let's say 5,000 kilometers. The 7 minutes is 4,000 kilometers. And the 1 minute is, let's say, 1,000 kilometers. All right. So what you do is you get a compass, all right, a math drawing compass, and what you're going to do is you have a scale. So let's have a scale down here. There'll be a scale on the map, all right, and the scale will be like 1 to 10,000 or 1 to 100,000, whatever it is. Okay, the scale ratio of the map to real life, and you basically have your ruler or you have your compass, and you have the scale. So say this is 0 and this is 1,000, 2,000, 3,000, 5,000. So this one's 5,000. Okay, so you have your scale. It's the same. It's not really, but it's the same. Hit your compass, and let's take New York and New Jersey first. You have 5,000 kilometers. So you put your point of the compass on 0, and then you widen or spread out your compass so the other point where usually the pencil is on the 5,000 point there. Then you take your compass, which is this distance, right, which makes your radius of your circle. You put the pointy bit, the 0, on New York right here, and you would draw your circle like that. Actually, it would be like this. So I've drawn the red line for New York right here, the red dashed line. That's my circle I drew with my compass. Now, obviously, it goes off the US map, okay, into like Canada and down to the Gulf of Mexico, but you just want the part. We know it's in America somewhere, the 48 states. We don't know where, so we want the area, the line going over the American map right there. Do the same thing for Chicago, and let's say Chicago, the line does this. Okay, because it's a bit smaller, isn't it? This is 4,000 kilometers. One for Chicago, so it'll be smaller. So it's a smaller circle that you draw. It's a shorter radius. Now, let's just back up a second. I just drew the New York one, right? So in theory, the earthquake could be anywhere along the red line over the country, anywhere. Now I've drawn the one from Chicago. Now, in theory, I've got two possible locations. One here where they intersect, and one over here where they intersect in the Gulf of Mexico. So because I have one circle, I have endless possibilities around that red circle. Now I've drawn two. I've now narrowed down that endless possibilities to possibly 2 or even 4 on the other side. So a lot down to 4. Now, when we add in the Californian one, and I'll use green for this one. Okay, so the California one, just not to scale, just California one. There we go. So drawing the green line for California. Now it's a lot closer based on the 1,000-kilometer distance from the epicenter. But now look, right in this area here, I have the 3 circles intersecting or overlapping. And I have a triangulated location using 3 separate seismic stations of where this epicenter is of the earthquake. Now let's just say it was in northern Colorado. So to say that it's northern Colorado, which can happen, but it's rare. All right. But yes, that'll be the location. So we're using 3 stations to locate the epicenter of the earthquake in more detail. And we've used the seismograms, we've used the time travel graph to figure out distance, and then use the distance on the map with the scale to draw our 3 circles with the compasses so it's accurate. And we have located a, not exactly pinpoint, but definitely a location of that epicenter. Now we can tell based on location whether it's a populated area near any kind of infrastructure or a certain kind of geology, a certain kind of rock that would amplify or cause different hazards like rock falls, landslides, liquefaction, that kind of features and hazards that can be done with different kinds of rocks. And yeah, that's basically it. So hopefully that helps with the lab, guys. And anything you need, please add a comment, please subscribe, and check out the more videos on earthquakes and everything to do with earth science and geoscience.